can finish it today, it will be fine, otherwise we will continue it in the next class. Obviously, it is going to be a very brief introduction to the subject, because it is a full-fledged subject by itself and can be taught in a full semester course. So, we will be essentially dealing with the rudiments of error correcting codes. What are the basic ideas behind it? Okay. What we have learned from our discussion so far is that use of redundancy is the clue on which Shannon's breakthrough result is based. That is, if we want error-free communication of information, we have to add redundancy to our signal, to our message that we are transmitting. So here is also some food for thought, that on the one hand we have the source coding problem, in which our effort is to remove redundancy to as much as possible, right? Because we want to represent the source, obtain a digital representation of the source output efficiently. We don't want to start putting redundant bits unnecessarily on the channel. On the other hand, if we want our transmission to be robust against errors in the presence of noise, we want redundancy to be present there, right? It of course does not mean that we can do away with source coding, right? Because the redundancy that is present by inefficient representation of the source is not something that you can utilize, right? So what you really have to do is do source coding and then also introduce redundancy in a controlled manner, in a manner that will allow you to make use of redundant information for removing errors separately. So really speaking, in an overall digital communication system, you have two kinds of encoders and decoders present, right? Two kinds of encoders at the transmitter and the corresponding decoders at the receiver. The source encoder, its job is to obtain or give you an efficient digital representation of the underlying messages being emitted by a source. On the other hand, the so-called channel coder is the one which will introduce further redundancy in the transmitted message, so that you can control the errors or be able to detect and correct errors that take place, so that you can ultimately hope to get transmission of your information with as few errors as possible. Okay? Theoretically, even error-free information transmission is possible. So this is the basis for going for error correcting codes, that we must have a channel coder which is able to add redundant information in a controlled or desired manner. Okay. Now there are two kinds of block codes. We will talk about two kinds of codes. One are called block codes, and the other kind are called convolution codes. For lack of time, we will not even touch convolution codes. Okay, but let me just give you an idea as to where they are useful. Convolution codes, some people, according to a school of thought, are really a more powerful class of codes, because they are able to take care of not only additive wide Gaussian noise channel situations, but also some certain other kinds of channels. For example, what are called burst error channels. Okay, but in addition to this, there are some differences of opinion as to whether block codes or convolution codes are really superior with respect to each other, or ultimately they are all the same. But other than just these few words, we will not really touch upon convolution codes at the moment, and we will be essentially dealing with block codes, where basically what you do is your coding is carried out on a block by block basis. If you remember the argument that we used for proving the concept of channel capacity, Shannon's concept of channel capacity, that argument was asymptotic in nature, right? We had to we were accumulating data bits, information bits, before we carried out the coding, right? and in the ideal situation, in the asymptotic situation, we are accumulating infinite number of bits before you carry out the coding, because we are taking alpha t bits, information bits, and coding it into a block of beta t bits. Of course, that means working with infinite block lengths, infinite information sequence lengths, which is impractical because it means infinite coding delay and corresponding decoding delay, right? So more realistic block codes accumulate information bits up to a finite number, right? Say you take k data bits or information bits. I'll be using this word data bits or information bits rather interchangeably from now onwards, but when I say data now, I'm talking of information data, information carrying data or information bits, and these will be encoded into a block of, so you will be taking a block of data bits or information bits and encoding it into a block of code bits, so called code bits, which will obviously be larger in number, right? So corresponding to k data bits, we will have n code bits. This is the basic idea of block coding, where n is typically greater than k, and this will bring down your effective information rate, right? That's the whole idea of Shannon's channel capacity channel capacity theorem, which says that if you keep your information rate below a certain value, then there is a possibility of error-free communication, right? So this obviously will bring in that required reduction in the information rate, and your resulting what we call code efficiency, which we also talked about earlier, will be obviously k upon n, because total message length is of n bits, out of which the information carrying bits are only k in number, so your code efficiency is k by n. And such a block code is usually denoted or called an n k block code. This is a usual terminology for such a block code. More precisely, the coding procedure consists of taking a sequence of k bits, data bits, which we can denote as a vector d1, d2, d sub k, and map it. This is what the coder will do, into a vector or sequence of code bits c1, c2, c sub n. Okay, this mapping is what is going to be done by the so-called channel coder. Or channel encoder. Okay. Now, the first thing that we must answer or discuss before we proceed further is what should be the relative values of k and n, because this is the first crucial thing to.
Isn't channel efficiency same as code efficiency same as channel capacity?
No, code efficiency is not same as channel capacity. So code efficiency will have to be less than channel capacity, right? But it is an attribute of the code. Is it clear? It's an attribute of the encoder that you are designing, but its design requires that you keep the channel capacity in mind while you are designing. Okay.
So we have source encoder and channel encoder,
Yes.
both of them separate.
Right.
So the product of the efficiency should be less than channel capacity, or both of them should be
Code
separate.
efficiency at the maximum can be equal to channel capacity.
No, as far as these k bits are concerned, they are supposed to represent your source output. It is assumed that you have done the best possible thing as far as your source coding is concerned in the matter of this representation, right? From now onwards, we have kind of segregated the two problems. We are only looking at one problem at a time, because they are really separate problems, right? If some redundancy is still there, that will go on, but we are not going to be able to make use of that redundancy.
Okay, we are not going to make that use.
That's right. I mean, there are some proposals and schemes and suggestions where people have tried to argue, why not use a redundancy that is inherently present in the source itself to to carry out error correction and detection. But that kind of scheme has not been perfected yet. I mean, the theory of those kinds of ideas has not been worked out very nicely. Okay, so at the moment we have kind of segregated the two problems, and this is how most of the real life systems work. The source encoding process is decoupled from the channel encoding process, and the corresponding decoding process is also decoupled. Okay, so does that answer most of the questions that were raised? Fine. So we will take up this question of what should be the relationship between K and N. How we should. Now this is really see in real life we will not really try to, when you try to design an encoder or a decoder, our purpose will not be able to obtain error-free communication, because that we know is only possibly a theoretical possibility rather than a absolutely real possibility. But we will try to go as near to it as possible, and one way to do that would be to make sure that if a certain number of errors occur whose probability is relatively large or significant, then we like to make sure that any error pattern up to a certain length we are able to detect and correct it, right, which will effectively take care of most of the commonly occurring kind of error situations, and therefore effectively reduce your error in information transmission. Okay, so one of the most commonly used criteria will be to be able to detect or correct a certain number that you have decided, say T, that take place on the channel. So you are transmitting a code of length n, and there is a certain small probability that up to T errors can take place, because let us say the probability of having more than T errors, it becomes so negligibly small that it is of practically no importance to us. So we decide on this number T which is important to us. It will depend on the channel conditions, right. If it is a very bad channel, then T can be large. If it is a relatively good channel, T can be very small, right. We can have a very small value of T, and that is good enough for us. So once we decide on this value of T that is important, this becomes our crucial design parameter for the encoders, channel encoder. So we would like to have a relationship between K and N in terms of this parameter T. Okay, how many errors, up to how many errors we want to be able to either detect or correct, right, depending on whether you are going for error detection only or error detection and correction. To answer this question, let us first pose a more limited question of what is the minimum number of in fact this is a question I am rephrasing here. Minimum number of check digits required to detect or correct T number of errors in an NK code. Right, this is the question of interest to us, but to answer this question, let me do a bit of combinatorial counting of a different kind of question. Start from the total. Let's start by counting the total number of available code words. When I say available code words, you please imagine the same n-dimensional hypercube that we have been talking about in the past. We have n bits, n code bits. We can think of these n code bits as vertices of, appropriately chosen vertices of an n-dimensional hypercube, right? Fine. How many vertices are available? This is what I mean by total number of available code words. The vertices which we can use as code words, sequences which we can use as code words. We have a choice of from 2 to the power n possible vertices, right? Out of which how many we should really select as code words? Actual number of code words will be 2 to the power k. Let us say a particular code word is transmitted. Let the transmitted code word be some code word which will denote by Cj prime. Cj. And let us say the received code word, please ignore the prime here, the received code word is Cj prime. If no errors occur on the channel, Cj prime would be precisely the same as what you transmitted, Cj, right? What we now have is a situation where we have agreed that we can expect up to a certain number t of errors in Cj prime with respect to Cj. Okay. So if the channel introduces or causes less than or equal to t errors, okay, it implies that our Cj prime will lie within the Hamming sphere of radius t around the code vertex Cj, transmitted code vertex Cj. Alright? Cj prime in that case lies in within the Hamming sphere of radius t centered around the transmitted code word C sub j, right? And this also implies that, as we have discussed earlier, that we should not use another code word that we choose as another vertex which we choose as a code word should also similarly be, how far removed it should be from this code word? No, if you want to be able to have Cj prime corresponding to Cj lie within its own Hamming sphere, within the Hamming sphere of Cj, and similarly all t or less distant received code words from other code words also to lie within their corresponding Hamming spheres, then it means that these various code words must be separated from each other by a distance of 2t plus 1, right? 1 the code word and all 2t distant around it should not be code words, right? So it implies that we should not use another vertex lying within a distance of 2t plus 1 around Cj as a code word. Fine. Because we want these two t radius Hamming spheres to be non-overlapping with respect to each other. Basically, that's a consideration. Therefore, that implies that the minimum distance, this is what we call minimum. Actually, when I said distance here, the measure of distance is in the sense of what we call Hamming distance, right, which we have been talking about in this context. It's defined as the minimum distance between t error correcting code words and that should be equal to 2t plus 1. This is an important result. So we have not yet answered the question of what should be the relationship between n and k. We started with a more limited understanding of what should be the relationship between various code words, right? If we want T error correction capability, then the various code words that we select should be such that their minimum distance with respect to each other in the Hamming sense is at least 2T plus 1. Okay. Now this will take us further to the relationship between n and k that we are looking for.
N minus k equal to 2t plus 1.
We'll see that. Is that understood? Is there any question about this conclusion that we just drawn, that for error correction up to T errors, the required code should be such that minimum distance between any two code words of the code should be at least 2T plus 1. You have two spheres, you are drawing sphere, the centers are somewhere, and you are drawing, mind you, this T is an integer, remember that, T is an integer, right? You are drawing two spheres of radius T around each of them. What is the distance between the centers? They obviously cannot touch each other, so it is 2T plus 1. That's the basic idea. Okay. Therefore, to answer what should be the relationship between n and k, we first now take up. Very good. We first look at how many vertices will lie in each of these spheres. Then only we will be able to see what should be the value of n. Right? So the next question we address is how many vertices can lie within a Hamming sphere of radius T. Okay. All right. What is the characteristic of all these vertices which lie within a Hamming sphere of radius T? We can think of them as if they are obtained because of errors in the channel on the basic code word, right? And errors are up to maximum of T. Let us look at number of sequences that we are possibly likely to get, number of sequences of obviously n bits, because we are talking of code words, that differ from C sub j, the center code word around which the sphere has been drawn, that differ from C sub j by j bits, okay, where j is obviously less than t, because when you say up to T errors, remember we can have T errors or less. So I am considering at the moment a number j of errors which is less than t, then we will sum over j. What is this number? Consider this number. It is the number of n things taken j at a time, right? So obviously the answer is NCJ. Okay, is it clear? You have n things and you are looking at how many ways you can take out j at a time, j things at a time. In how many ways you can take out j things. Now, therefore, that implies that the number of ways in which T error up to T errors can occur what will be that? That's right. You take n sub NCJ, j equal to 1 to T, not 0, because 0 will include the code word.
Sir, but that is also in the sphere.
That is also to be included.
Yes, that's in the sphere.
That has to be included.
I was going to bring it in later. Let's at the moment I'm counting the number excluding the code word here. Okay. And this is the, therefore this is the number within one sphere, and we have how many such spheres? 2 to the power k, right? So now let's count our total number of vertices, right? So for each code word, for each code word we must have, that is, each vertex that you select as a code word, you must leave out so many vertices in the neighborhood unassigned as code words. Is it clear? We must have NCJ j equal to 1 to t number of unassigned vertices. Right?
So the code word, original word,
Yes.
j, it is already included in, like for any given value of j,
Yes.
NCJ is the number of possible other sequences which can come around it.
Right.
If j bits differ, that
Correct.
includes the CJ also.
No, but I am not taking j equal to
j equal
0.
to 0 we are not taking, j equal to 1.
That would include that if I include j equal to 0, which I will do later, because this is the number of other sequences which differ from it in j places. If it is differing from it, cannot include it unless j is equal to 0.
No, what I meant was then, for instance, if j equal to 1, you have the value is n,
Right.
and you have the length of the sequence is n bits. So if it differs from it in 1 bit, it could be in the remaining n minus 1 bits and not in all n bits. So there are n
No, no.
minus
When I
1
say n sequences, this means there are in the neighborhood n sequences that differ from it in one place.
that means total sequences and this one.
Not total sequences. Why are you getting confused? We have, let me draw a picture. We have a center. We have a center. We have all kinds of sequence vertices in the neighborhood, right? Those which are at distance unity, that is, they differ from it only in 1 bit. Those which differ from it in 2 bits. Those which differ from it 3 bits, right?
All I'm saying is if j equal to 1, that means there are n different combinations.
There are n other
which
sequences
differ from it
which
by
differ
1
from
bit.
Cj in one place.
That means should there be n minus 1 such? Should there be n minus 1 such sequences which differ from a given sequence if the length of the sequence is n bits?
ठीक है.
Why n minus 1? It should be n only.
In the remaining n minus 1 places,
Yes, sir.
that place is, I mean, see if you have
I don't know
So
what you're
you have
saying.
neglected the code.
Suppose I have a particular sequence, right? I can construct n other sequences by replacing one of these bits by the opposite bit. So what's the problem? I can construct n other sequences by replacing any bit by its complementary bit, not n minus 1. Okay? This is okay. I mean, this is basically using combinatorial theory, but you can work it out otherwise also. Alright. So if, does anybody else have this confusion now? Fine. Let's now do the counting. The counting is our total number of code words that we must have, total number of vertices that we must have, must be the total number of code words plus what we have to leave unused, right? So total required total number of words or total number of vertices, words or vertices you can use interchangeably. This will be equal to 2 to the power k.
into 1 plus.
Just a second. This 2 to the power k is the number of code words themselves, because I require 2 to the power k code words. Plus, for each code word, I require so many unassigned vertices. Right? This is the total number of required vertices in that n-dimensional hypercube that I have. It must have at least so many vertices. For such a code to be feasible, such that minimum distance between any two code words is 2t plus 1. Okay? For a code of this kind to be possible to make, I must have at least so many vertices in my hypercube. Is it clear? This 2 to the power k term is the number of code words itself. Then for each of these code words, I have so many unassigned vertices. So for 1 multiplied by 2 to the power k code words, this is the number of unassigned vertices. This is the number of assigned vertices. Total number of vertices must be the sum of these two. Okay? So that implies that 2 to the power n should be greater than or equal to 2 to the power k. As you can see, I can take 2 to the power k, factor out, I will be left with 1 plus this, and I can include that now in this summation by putting j equal to 0. which is the same thing that you were saying more or less. That is our result, okay, which is sometimes also put in this way: 2 to the power n minus k is greater than or equal to this. Tells me if I want a t error correcting code, how many check bits, n minus k is the number of additional check bits or redundant bits that I am adding, isn't it? N minus k, so let me call this m. What should be the value of m such that I get the error correction capability? Okay. This result is known by Hamming bound, by the name of Hamming bound. Okay. So it's not an explicit relationship, it's a somewhat involved relationship, but one can tabulate it out, right? For a given value of t, one can work out the combinations of values of n and k for which this relationship will be satisfied. For a given value of t and k, you can determine a corresponding value of n, right? Or in any other way, in any combination that may be of interest to us. Any question on this result? No.
But can a code be found for this value of m?
That's a very deep question. I cannot answer it straight away, but codes do exist for such values of m. He is asking me whether I can guarantee the existence of a suitable code for this thing. Well, the existence is obviously there,
But
because
for a larger value of m. This is a bound, sir, but it does not ensure that code will be found for this.
it depends on what you mean by finding a code. If you say whether you can find a code with a particular nice structure, then it's a difficult question to answer. But if I just say whether it's possible to find a code, I already know that it exists because this bound has been obtained on the basis of a construction. The construction procedure is I'll choose an arbitrary vertex, leave out so many vertices unassigned, right? Then go to the next vertex, and by construction I can always go ahead and do it. But it may not be possible to form a nice linear structured code or any kind of structured code. That will depend on the kind of structure that we are employing. Okay, so at the moment the answer is yes, it is possible to find a code. How easy or difficult it is to implement it is a different matter. Now similarly, if you are only interested in error detection and not error correction, there are certain kinds of communication systems, particularly where reliability is poor, where one does not really entirely rely on error correction, automatic error correction, where you would rather retransmit a message if too many errors have been detected, than just do automatic error correction, because there can be a lot of problems with that kind of situation. These kind of communication systems are called ARQ systems, automatic repeat request systems. They prefer on error detection ability rather than error correction capability. Okay. For that we require code with minimum distance t mean prime equal to, this answer should be obvious. If I only want to be able to detect up to t errors and not have the capability of correcting them, t plus 1, right? Is it obvious?
Because we can have overlapping in that case.
All you want to make sure is that you are able to detect it. So the answer is t plus 1. Okay. Now let me come to some basic theory about block codes, their construction and their decoding. Now the subject of block coding is a very highly developed subject today, and essentially what it really boils down to is finding mathematical structures which will enable simple are reasonably simple implementations of code generation as well as decoding for codes which have good properties, good error correcting properties. Okay. So basically what I am trying to say now is, so far we have only talked in an unstructured manner, that we have a n-dimensional hypercube and somehow we have to assign those vertices as some of those vertices as code words and leave the rest of them unused. The question is, how do I go about selecting words, which words should be code words and which should be left unassigned? That is what coding theory is really all about, right? How do you carry out that design of assigning the proper vertices as code words and leaving out the rest as I mean, that's what theory of error correcting codes or error control coding is all really about. Now, one popular structure which is more or less the basis of all error correcting codes, most error correcting codes, I should not say all, is the linear structure, linear block codes, just the structure of linearity, where basically the idea is that a code vector C, C1, C2 to Cn, is obtained from a data vector D, D1, D sub 2 to D sub k, essentially by taking a linear mapping of this data vector from a k dimensional space to an n dimensional space. Okay. Just essentially each code bit is taken as some kind of a linear combination of the corresponding information bits. But mind you, we are now working with not our normal, our field of operation is not the normal real number field in which we carry out these combinations, because these are binary numbers. Okay. In binary numbers we have a separate field of operation which you are familiar with. It's called the Gelbach field. Okay, where basically addition is done modulo 2, right? But there are many other properties associated with this field. I am not really going it. A proper study of coding theory first would require us to study this field theory fairly thoroughly, but we don't have time for doing all that. With whatever rudimentary knowledge you have about modulo 2 addition and all that, we can study our basic theory on that basis. Okay. So in this field the linear combination operation is essentially an exclusive bit by bit exclusive OR operation. Okay. So when I say take linear combination of these bits, it only means I am taking some D1 plus D2 plus D5 and things like that, this plus being really an exclusive OR operation, right? Because basically addition is modulo 2 addition. Now out of all the this big class of linear block codes, there is a subclass without any loss of generality, and this subclass is known by the name of systematic linear block codes. We will discuss these. In the systematic linear block codes, the first k bits of the code are taken identically to be equal to the corresponding information bits themselves. Okay. So C1 is not taken a linear combination of these, but C1 is taken as simply equal to D1. C2 is taken as D2, and so on up to C sub k. That's taken as D sub k. So the first k bits of the code sequence are the same as the corresponding information bits or data bits which we are trying to encode. Mind you, this is the input to your encoder. The vector D is the input to your encoder. The encoder is a mapping device which converts this k bit input sequence to a C bit to an n bit output sequence C. Right? The systematic linear block encoder will first produce the first k bits straight away in this manner. Practically no processing is required there. Okay. For the rest of them, it does the linear combination. So Ck plus 1, for example, could be H11 D1, H12 D2, H1k dk. Okay, where H11, H12, H1k are, so we are taking some linear combination of these k bits. These are the coefficients of linear combination. Obviously, because you are working in a modular 2 field, these coefficients also take on values only between 0, the two values 0 and 1, binary values 0 and 1. Alright, d1, d2, dk obviously takes 0 and 1 values. So, these operations are essentially modular 2 operations. These are some coefficients of linear combination which you have to select, right, which will depend on the design of the code. Similarly, ck plus 2 will be given by H21 d1, H22 d2, H2k dk, and so on. Finally, C sub n will be Hn1 d1, yeah, this should be m. I'll call that m. You are quite right, because there are only n minus k check bits, and these are the check bits, these are the data bits.
So the operator you use, what did you say? What is the operator?
This operator is a exclusive OR operation, modular 2 addition, right. Now, obviously, this mapping from the vector D, you can see each of these C's, each of these components of C depends on essentially this vector D, right. I can express it in the form of a linear mapping. You know how linear mappings are described mathematically, algebraically? By the use of matrices. So, best thing is to use a matrix representation for this set of equations, which you can write something like this. The code vector C is the data vector D multiplied by the mapping or so called generating matrix G, okay, where G, the structure of G, let me see whether you can see. I have taken C and D to be what kind of vectors? Row vectors, right. These are row vectors, and alright, let us see whether you can tell me what is the structure.
E into K unit matrix.
Right.
And then the other X matrix.
Is that obvious? And this will be H11, H12 to, actually around column I will go H12 to H1k, and this will be H12, H22, this should be H21, I am sorry, H21, H22k, and this is HM1 to HMK. Because imagine you have a vector, you have a row vector in front of it, right? That is D1 to Dk. C1 is equal to D1, C2 equal to D2, C3 is equal to D3, right? And do I need to explain this? I wish this.
So it should be in the column, sir. So it should be below it.
Because of the structure you have taken.
No, I have taken C and D to be row vectors. If they were column vectors, what you are saying is right, right? Remember this, C and D are row vectors and the equation is being written like this. What you are normally used to it is writing it like this, they are being column vectors, okay? So just keep that in mind while, unfortunately the space is a bit limited, I can't display the two together, then it becomes obvious. But you have them in your notes, so I think you can see it from there. So I can write this as a k into k unit matrix. This is k into k, and this is some matrix which we will call matrix P. It is known by the name of check matrix. Its dimensions are k into m, k into n minus k, and this matrix is known by the name of generator matrix, matrix G. So, a systematic linear block code is essentially specified by the specification of an appropriate G matrix, generator matrix. Okay. That is as far as the basic definition is concerned. Any questions? I will give you an example of a
So
six.
there will be a
Yes.
limitation on the choice of the values of the set.
Limitation in what sense?
They have to be kind of independent of rows. You can't have two code
Two
words.
rows
Can't have
similar.
a same
Same there.
checkbooks.
Okay, now you are saying how one should select G,
Yeah.
right? So that is a matter of designing such codes. We are not at all touching the topic here. Okay.
So two columns should be different.
There are lots of things we have to study rather than making just statements of that kind. You have to really study the structure of G very thoroughly, and then understand it in terms of what properties we want from it, right? And then only be able to say something very definite. Yes, some of the stipulations you are making may be correct, but unfortunately I cannot take up that for discussion here because of lack of time. As I said, this is a full-fledged subject by itself, and proper study of that would require you to study finite field theory, right? Because in fact we may not always be working with only binary numbers. We may be working with Emery numbers, where m is some power of 2. And first you have to understand the theory of numbers in that field, and then only we can do a proper study of error correcting codes in a very general way. But even for the binary field, right, G of 2, Galois field with a base of 2, one has to understand what that field is all about, what are its properties, and then how do we study the properties of such matrices G in that field. So I will not really go into all that detail, which for those of you who are interested can perhaps hope to take a course in information theory and coding next semester if it is offered, next or next to next semester. At the moment, I only want to give an idea that using such things, how can we go about encoding and decoding, right? Basically, suppose we have a code like this, how do we decode it? Those kinds of things are all I can cover with this. But before doing that, I think I will try to finish this talk today by just taking a simple example of a 6-3 block code. Where G is one zero zero 0 1 0 0 0 1. This is your I3, right? And the parity check part, this P matrix is sometimes called the parity check matrix. We will see the reason for that. For one, it's obvious that it is generating the check bits, right? So for that reason, it's called the parity check matrix. But it has some other physical significance in decoding, which we'll take up when we talk about decoding. Okay, so this will be we have to specify the P matrix here. Let this be given by this 1 0 1 0 1 1 1 1 0. So that's a 3 by 6 matrix corresponding to a 6-3 code. You can now generate a mapping of this kind. If the input sequence is 1 1 1, your D1 D2 D3 is 1 1 1. What will be your output code sequence? It will be 1 1 1. The first 3 bits are going to be the same. The next one is going to be all other 3 will be 0, right? Similarly, if it is 1 1 0, this will be 1 1 0. This will also be 1 1 0, and so on. You can construct a table of 8 code words. I think I'll just stop here, and next time we'll discuss. Suppose I have a linear block code, systematic linear block code, which has this structure. How do we do the decoding at the other end? Okay. Is tomorrow on or off? There is a class tomorrow.
Tuesday schedule.
Tomorrow we have. Is it been announced?
Yes, sir.
Because I don't know what it is. So I think then we'll try to finish it by tomorrow, and Monday, if you want, we'll meet. Otherwise, we'll have a break.
Monday is free.